thanks all of the attendees for joining us for the, probably the last space webinar for this session this year. And this time we're very honored to have invited Prof. Chun from Seoul National University, South Korea, to give us this wonderful talk today. Let me just do a quick introduction to Prof. Chun. Seong is currently Associate Professor of Department of ECE at Seoul National University. In fact, Prof. Seong also received his bachelor degree from the same department and same university. And later, he also received his master degree and PhD from University of Michigan, Ann Arbor. Prof. Chun has received many awards, academia awards, including the 2010 Society of Nuclear Medicine Computer and Instrumentation Young Investigator Second Place Award, and also 2015 Bruce Hasegawa Young Investigator Medical Imaging Science Award from IEEE NPSS. So today, Prof. Chun's topic title is Towards Deep Learning-Based Image Reconstruction with Model-Based Self-Supervision. So without further ado, let me pass the time to Prof. Chun, and let's welcome him for the wonderful talk today.
Thank you, Via, for such a nice introduction. Thank you very much. Hi, my name is Chun, and it's my great honor to give a talk in here. And I especially thank all the other organizers for this wonderful space webinar. And it will be a great opportunity for me to share my the research areas, and at the same time also get some feedbacks from you. I'm looking forward to that. So the title is something like deep learning based image reconstruction with the model based self supervision. But a lot of works actually are related just to the denoising and the self-supervision for the noise. But I'm also actually including some of the works that relate with the other types of the self-supervision too. So let's get started. So medical imaging is basically quite important for to address some challenges in healthcare. In order to, for the diagnosis and the treatment monitoring, for cancer, for the stroke and the heart disease, even the COVID-19 these days. And in order to get this such a nice image quality, people have been working so hard on this medical imaging, especially based on the so-called the model-based image reconstruction. Let's look at these two interesting figures. The left one is you have a spec image, and the left image is really blurred, and the right image, slightly, quite better in terms of the contrast. They are from the almost same data, but they are using just different algorithm. And on the right side, actually, this is another interesting figure from the Purdue University, and they are also looks quite different. However, they are also from the same data, but using different algorithm. The left one uses the so-called filter back projection, and the right one is actually the model-based image reconstruction. So essentially, the model-based image reconstruction, requires a lot of computation, but because it actually utilizes the more imaging physics, so therefore it actually has such a nice properties. So let's actually go into a little bit deeper about this. And this one is actually kind of the simple schematic for the model-based image reconstruction, or I say the computational imaging. So usually the question mark here is the unknown ground truth or unknown image that we want to visualize, and then imaging will be done using some hardware, so-called the precision physical apparatus for imaging, and then it will actually have the coded measurement. It can be image, it can be just a measurement that a human cannot really interpret. And then after some algorithm or computation, hopefully we can get some image that is close to the underlying image that we actually wanted to visualize. And this is actually the whole schematic. And in the past, actually, just the measurement itself usually becomes an image, but it actually it requires more and more computation in order to overcome some of the limitations like noise, some of the limitations like undersampled data or something like that. So therefore, usually the precision physical apparatus can be modeled well using some mathematical analysis. So we can usually obtain the very nice accurate forward modeling. And this can be just approximated using some linear model. It can be also actually realized using the full Monte Carlo simulation. And this coded, I mean, after you have this coded measurement, usually you want to go back to your own image. We call this inverse problem based on the forward model that we just had. However, usually this inverse problem is ill-posed, so therefore we need additional regularizer based on the prior models for image, or sometimes motion, or different types of the underlying parameters that we are interested in. So therefore, this is a kind of the basic component that we have in terms of the model-based image reconstruction. And then the algorithm usually requires to run some optimization in order to solve this nice inverse problems. And other types, so most of the model-based image reconstruction that I have been studying was actually about some tomographic image reconstruction problem, like positron emission tomography, or SPEC, the single photon emission, computed tomography, or even the low dose, actually the computed tomography or X-ray CT. And then these types of schemes also has been applied, or has been also been popular in the MR reconstruction, especially the fast MR reconstruction, since the advent of the compressed sensing theory came out. So one of the first application for the compressed sensing, as you may know, was the fast MRI. So these types of the having data fidelity term, having some prior term, and then based on those models, formulating the model-based image reconstruction becomes a quite popular forms of the forming the images. So of course, these types of the computational imaging not only limited to it's not just limited to the medical imaging, but it also has been applied to many different areas, like super resolution zoom imaging in the smartphone, or microscopy, or even black hole imaging these days, or the lensless camera or lensless imaging for different applications. So this type, they are all using different, of course, the imaging systems. Maybe you're using the different algorithms, but the principles are quite similar, using data fidelity term, using image, prior model in order to formulate the inverse problem to solve. And since the AI came out, the deep learning, I say, came out, the computational imaging actually has been quite different these days. So computational imaging finally meets the deep learning and the deep neural networks. I'm showing you the famous UNet, basically just revolutionize all these computational imaging field. The one problem that we had that in the model-based image reconstruction was the computation. So because it was using the iterative algorithm, it actually requires a quite lengthy computation. So therefore, sometimes you need a very fast result in terms of the imaging. So therefore, it requires to have the fast computation. And deep learning actually solves that problem quite nicely. So basic principle for them is quite simple. So you have just have an input. Input can be just a coded measurement. Input can be an initialized image that you can quickly obtain. It doesn't matter. And then you have a deep neural network, and then you have the output, and then you are comparing the output with the so-called ground truth. So as far as you have this clean image, you can always train the network. And then once you actually measure the error between the output and the ground truth, and then that error will be back propagated to the network to update the network weight parameters so that the network can be trained. And this simple and quite powerful structure actually has been applied to so many different imaging applications. So I'm showing you a couple of examples. So one example is the real image super resolution. So somehow they were able to obtain the nice ground truth image like this on the right side, and then the left side is a little bit below the input, actually low resolution input, and then the output of the network in this case it will be in the middle, which is quite close to the ground truth. So therefore, once you train the network, then you can actually obtain such a nice image quality using the deep learning. Another example is the image dehazing. So you have an input. I cannot even see anything actually in this case, but if you somehow, let's say that you can actually obtain this type of the ground truth, then you can train the network. So then the network output will be quite amazing in the middle. so that you can actually recover the all this information from the almost haste, quite hasty actually image in the input. So we also have a video deblurring example. So the input will be a quite blurred image in this case, but let's say that you can obtain the ground truth using the high-speed camera. Then in that case, the output can be obtained by training the network so that you can also obtain this nice result too. So, okay, so what's the problem then, right? So we have all the nice, deep learning, and then, the input and the output will be defined using the mapping from, using the deep learning. And then as far as we have such a nice ground truth, then we are done. Now the problem is actually the quite challenging problem actually to obtain the ground truth is, what if we don't have it, right? What if we don't have it? So let's actually go back to the original, the problem of computational imaging, or original problem of the model-based image reconstruction. As I said, we have such a nice hardware system to obtain to generate the coded measurement. Now, this coded measurement, actually, we want them to go back to the original image by using some computation. So if this computation is easy, then we don't have to worry about it. Now the problem is, what if this computation actually is solving some quite ill-posed inverse problem? And this ill-posedness actually comes from many different points. One example is the noisy measurement. If you have a noisy measurement, then you somehow has to deal with the noise in order to make this problem well posed. So that's a quite actually big challenge in many computational, model-based image reconstruction. Another case will be undersampled measurement. What if you just have an undersampled measurement and then you want to actually obtain the clean image? So that's actually another big challenge to obtain the clean ground truth. We can also sometimes have some artifacts like a motion, or even sometimes have artifacts coming from the scatter actually in imaging. So therefore, there are many challenges to overcome in order to obtain the clean ground truth. So for me, actually, when I first actually encountered this such a nice deep learning, I was thinking that, okay, do I really have a clean ground truth in many imaging? In my imaging system. So in my case, I was doing a lot of the molecular imaging, like PAD or SPECT. So obtaining clean ground truth for me was quite challenging. So therefore, okay, so if I have this imaging system, I need ground truth, right? And if I want to have the deep learning based nice imaging system, then I need the ground truth. But in order to obtain the ground truth, I need a nice imaging system. So therefore, this is like a chicken egg problem for me. So therefore, I was kind of interested in deep learning based, deep learning training without the clean ground truth. Another challenge probably was some sort of like a black box model of the deep learning. So deep learning have a nice input output, but we don't know what's going on inside. So therefore, what if we have just knowledge about the imaging physics? What if we just want more robust result? So always guaranteeing, or at least interpret the result for the deep learning. So therefore, this AI-based computational imaging with models also has been kind of the one of my interests that for the computational imaging in that case. So, okay, so I cannot solve all the problems at the same time, of course, right? So therefore, I was kind of interested in the one by one. So, okay, let's go back to the easiest problem, or the most fundamental problem that and then the problem that I chose was the denoising. So therefore, you can see that we can have a deep learning based denoisers. The input will be noisy image, probably the output will be a clean image. Then usual supervised training requires you to have clean ground truth, and then usually the ground truth will be paired with the noisy image, and you need a massive amount of them. So that's usually supervised training. But what if we just don't have this clean image? And maybe one way you can do is, okay, I have just one noisy image per clean image, and then I have a massive number of them, or I can just have a pair of independent noisy realization per clean image, and then I have a number of them. So those are kind of the problem settings that we had in early 2018 or around even late, actually 2017 probably. And then another problem probably will be, okay, what if I just don't have any image? I just have the undersampled compressed sensing measurement. Then what should I do in order to train my denoiser? So those are kind of the problems that I had very interested, and then I had been working on since around like 2017, 18, 19 or something like that. So let's actually just define the problem first. So the noisy image model will be just the active Gaussian noise in this case. So X in here will be a clean image, and then N will be a noise, and then Y will be, let's say that's a noise image. And then the denoising problem in that case will be a given Y. I want to obtain some image that is very close to X. So I'm gonna call this estimation to be X hat in this case. So that's the denoising problem. Then, of course, we can have a lot of different scenarios or cases. The first scenario will be we have a supervised training. So we can train a network with the pairs of X and Y, where these X and Ys are, we have a number of them. We have M number of them, I say. Then in that case, we can probably train the network pretty well, no problem. What if we don't have X, but instead we just have the YI prime, where YI prime is another independent noise realization of X, okay? So that's actually the scenario number one. Scenario number two, I don't even have a YI prime. What should I do? Okay, so those are kind of the scenarios that you may want to remember for next couple of slides. Then these types of the deep learning based denoiser, just same as the ordinary, the AI-based computational imaging framework that I just mentioned. But instead of having, but in here, we just have a noiseless image, and the input will be noise image. That's it. But of course, we don't know what if we don't have any X, then this is going to be the kind of the chicken egg problem, right? In order to have such a nice denoiser, we need a clean image. But if we have a clean image, then why do we need a denoiser or something like that? Okay, so that's a kind of the chicken egg problem that I mentioned. So around 2018, now it's really past, right? In terms of the deep learning, in terms of the advance of all the fast growing AI community, I say 2018 is a kind of the old method already, but let's actually talk about it anyway. So there were actually two different methods that came out at the time. So noise to noise came out from the NVIDIA at the time. And then we also studied the time unbiased risk estimator, and then using them to train the denoiser without ground truth. So the noise to noise uses the two independent realizations. So it has some limitation in that sense. However, it has such a wide range of applications, like different types of denoising, even in-painting problem, Monte Carlo rendering, and the MRI recovery. In the case of the SURE-based method, only one realization is required per image. However, it has only a application of Gaussian denoising, okay? Later, we extended to Poisson, compressive sensing or MRI recovery later, but still, it was kind of limited in that sense. So, by the way, actually at the time, we actually submitted to the same conference, the ICML at the time, but ours rejected, and noise was accepted. The reason was, I think, the biggest reason was at the time, the performance was kind of underperformed at the time. So we actually improved the performance, and then that was accepted to NURIS at the time. So the noise is actually quite simple in terms of the model. So instead of using the regular loss function, L2 loss or L1 loss, usually L2 loss function. So with the X, we replace the X with the Y prime. That's it. And then it was working amazingly. So for the MRI recovery or the Gaussian, Poisson, and the even Bernoulli denoising. So it was working quite well. It has a very good impact, especially in the medical imaging, because it has such a nice and a simple formulation. So it has a wide application range. So let's actually talk a little bit about the Einstein's unbiased risk estimator. This is not what we are came up with, but rather it has been quite famous actually in statistics field. So let's say that we have a mean square error loss. You can see in here. And then it has an X clean image, and then it has the output of network, which is H theta, and then the Y will be input, which is the noise image for fixed X. So in that case, the SURE will be defined as follows. The SURE will be defined as the data fitting term, which is the Y minus H theta Y, which is the L2 norm of them. And then we have a minus a sigma square, and then we have a divergence term here. So that the divergence term will compensate for some noise deviation in that case. So can be a kind of working as a kind of regularized in that case. So one good thing about SURE is that we don't have X anymore. We only have a Y here, right? However, the following will be true based on the SURE work came out actually in 1981 in this case. So look at this. So the expectation of MSE will be the same as the expectation of SURE. So therefore, the SURE will be a nice unbiased risk estimator for MSE. So that's kind of the one principle that we used in order to train our network for denoiser. So therefore, we designed our SURE loss in this case. So it was working quite well. And this final SURE loss actually, we showed that actually they are the same. So the original risk function and the expectation of the SURE will be the same. Yeah, there's no approximation here anymore. Oh, except that of course we have, Gaussian noise model though, right? So we have a Gaussian noise model, but as far as it's satisfied, then this is actually exactly the same. And the SURE is following, but now one problem that we faced at the time was that the SURE loss should be used as a loss, right? In other words, if you want to actually train the network using any gradient-based optimization algorithm, then you need to actually take the gradient with respect to, take the gradient of SURE loss with respect to theta. So therefore, this divergence term is a kind of the hassle. So therefore, we try to approximate it using the Monte Carlo SURE. So this is actually the first order approximation for the divergence term here. Now we had to introduce our new parameter epsilon, but it was working quite well in that case. Okay, so this is a Monte Carlo SURE, so that's why we have been using as a loss function. So we actually studied a little bit about epsilon, and then it was working actually quite well for some cases where we have a smooth actually activation function, like in this case, smooth activation function. However, if you want to use some sort of like a ReLU or something like that, then usually we need to find a good epsilon, and then we actually fine tune it. I mean, we actually tune it later. And then it was also working quite well over the wide range of the sigma, wide range of the noisy levels. It actually always yielded a quite comparable result to the supervised training denoiser. Definitely better than the other BM3D in that case. Of course, for some limited data sets in this case. So if you look at the other result, then you can see that the BM3D sometimes actually have some blurred output because once they don't have a repetitive patterns, usually they are using Vino filter to blur them out, right? To get the PSNR, good PSNR. So therefore, even though they have a nice PSNR, sometimes they have some blurred output for the some non-repetitive patterns. However, for deep learning-based method, usually they don't have it anymore. So we have a usually very sharp result with the nice PSNR result in this case. So for BSD 68 data sets, we usually get better result than the BM3D, but quite close to the supervised case. But we still have some gap between them though. And this is actually the case where we are doing some fine tuning. So fine tuning here means that for the incoming test image, we actually run of several iterations of training to that actually the test image. Then in that case, we usually get better result in terms of the PSNR, and at the same time, actually in terms of the image quality. So look at this image quality, comparing with the ground truth, we have some nice patterns in the retina of this monkey. And this was not observed in the DB image prior or PM3D or other types of the denoisers, but we were able to get a little bit better, quantitative and the qualitative result using a slightly more computation of fine tuning in that case. So yeah, we've been talking about this, noise to noise. We've been talking about this SURE loss, and they were not really compared, but they just had a different ideas. And then the next step we were thinking was that, okay, then I want to study, and I want to compare, between these two methods, what's really going on there. And at the same time, another question that I can probably have was okay, let's say that I have a two noisy, but possibly correlated input. One example probably will be, I have some imperfect ground truth image, then I'm adding noise to make the noise image. Then in that case, two noise images will be correlated. So therefore, it can be just an imperfect ground truth problem with some mild correlation. So in that case, what's really happening? So that was one other study that we designed. And then the result was actually came out in 2019 DRIPS. So the first thing we did was we just need more explanation about the noise to noise. Nowadays, people are actually doing a lot of similar works like this, but at the time, the noise to noise was a really great idea. It was actually explained a little bit in the original paper, but it was not really fully explained in terms of the more rigorous derivation. So that's what we did actually at the time. So we started from the MSE, and then derive it, introduce the y prime, which is the another independent noise realization. And then what we found actually at the time was that as far as the y and the y prime minus x are uncorrelated or independent, you can always have this noise loss to be exactly same as your supervised loss. So therefore, that condition was extremely important. And now we can even actually extend further about this. So what if it's not correlated, right? What if it's not really correlated? And that part can be actually manipulated using the Stein's lemma if you are assuming that your noise is Gaussian. So that's the kind of the connection point between the noise to noise and the SURE-based method in that case. So that's what we did. So we extended a little bit about it, and then we finally found that this extended the SURE forms. We call this eSURE. And then notice that, they are really similar to the form of SURE. However, the one difference is the following. Instead of having one Y, now we have two Ys, right? So we have a Y1 and we have a Y2. And they can be actually correlated, and they can be even same. It doesn't matter. So if they are same, then the eSURE will be the same as just a SURE. However, if they are just simply correlated and not really the same, then you can separate them. And then let's say that I have an imperfect ground truth, which is a mildly noisy image. Then I'm adding more noise to train my denoiser. Then let's say that that's gonna be the imperfect ground truth will be Y1, and then the noise image will be Y2. Then in that case, Y2 should be fed into the network. So that's what you see here, Y2. And all the others, the Y1 will be compared in the data field determined here. So therefore, this extended SURE gives us more freedom to utilize the different types of, noisy realizations in that case. So, using this eSURE, we actually showed that this is exactly same as the supervised loss as far as Y1, Y2 are Gaussian noise, and then they may be correlated. So the result was actually working quite well. So this is a case where we have ground truth was mildly, it's not really mild actually, but it's actually corrupted with the sigma 10, and then we train our denoiser for the noise level over 25 and the sigma 25. So in that case, ours working definitely best. The noise to noise was supposed to not work well in here because of the correlation. So it doesn't necessarily mean that noise to noise is bad, but rather noise to noise was not really covering the case where we have two correlated noise. And then we also have an original SURE, but it was not working quite well because of the high noise level. So in that case, ours was working a lot better in that case. And then the PM3D, just the regular noisy images also, we outperformed that. So, this was a kind of encouraging. And then if you look at these types of, table result, then you realize that now our proposed method or issue method now is very close to the supervised performance. So therefore now, I mean, of course, this is synthetic Gaussian noise, but even still, that was a kind of the encouraging compared to our previous work on the SURE-based training. So therefore, it was working quite well. And then, this types of scenario can be actually can come out actually. If you think about how you are obtaining the clean image for the denoising problems, you usually use a longer exposure. It's not gonna be clean image forever. I mean, if you theoretically you always have to contain some level of noise, right, for your ground truth if you use a longer exposure time for your camera. But if you look at this nice result in the ground truth sigma 2b1, then you realize that using noise to noise worked quite well actually, comparable to the supervised loss. But even like a very small mild noise will actually degrade the performance. Especially look at the result of the sigma ground truth is 1, but the sigma noise will be 50. Then in that case, noise to noise will underperform a little bit more about it. Okay, so therefore, this types of in this kind of non-ideal scenario, our method was working quite well. So far, what I've been talking about was basically the let's say that I have a massive number of noise images to train. And then now let's actually think about what if we just have only one noise realization, just one single noise image. So when you think about like a BM3D or other types of conventional algorithms, that's always the case. You just have a one image, no training, it was working perfectly fine. So therefore, there was a desire. I mean, it has been quite desirable to tackle these types of the single image denoising problem. So in that, so people have been start to actually work on these types of problem in deep learning for the last couple of years. So one actually famous work was the self-to-self with dropout, which came out in 2020 in CVPR. So what they were using was actually just using dropout to make the multiple results for the single image denoising and then average them to boost up the performance. So they have such amazing actually PSNR, but instead actually requires such a long time to process the data. So that's a trade-off. But before this work, actually another famous work for the single image enhancement was so-called deep image prior. So let's look at the result first. So deep image prior actually has such a wide application areas like JPEG artifact removal, inpainting, denoising, and the super resolution. So it was working so well because the deep image prior was actually just about the structural regularization property of the deep neural network, especially the hourglass types deep neural network. So therefore, it actually has a variety of the application areas. So let's actually look at this the structure a little bit more carefully. And then this deep image prior, now input will be just a random vector. Okay, input will be random vector, and then there will be output coming out from the network. And this network, it's not just an ordinary network, but rather it's an hourglass time network. So you can think of it as a kind of UNet, maybe, right? Just reducing the dimension in the middle and then coming back again. And then now you are measuring the error, but the error will be measured between the output and now input. There's no ground truth. And but if you have just a good expressive network, then the output eventually should be the same as input, right? Because if your input was fitted to, if you fit your network to input, then usually you're expecting the output to be the same as input. However, interestingly, because of the structural regularization property of the deep image prior, the output cannot be input. If they have some corruption, then the corruption cannot be represented in terms of the deep image prior. So that was a kind of the amazing property. So what they were doing was that, okay, so now let's say that my input will be just a blurred image. Then later, people observe that the output will be not blurred image anymore, but quite sharp image. How about the in painting? Same thing will happen. For denoising, same thing will be happen. So therefore, people were very excited about this deep image prior as another possibility to be used for the imaging problems. So this is actually a one example that I brought from the deep image prior paper. This is the example that the deep image prior network was fitted to different targets. So the target here will be just image, or image plus noise, or image shuffled, or even just a uniform noise. If you observe that, and then you find that it will fit to the noise. It will fit to the image quite well, quite fast. However, if you want to fit it to the noise, then it has some reluctance. So therefore, what they were finding is that structure-wise, because of the structural regularization property, the deep image prior has some reluctance to be fitted to the noise. Eventually, may be fitted later, but it has some reluctance in that case. So therefore, by using these types of property, what they were doing is that they can just do the early stopping, so that the deep image prior network will be fit to the image, but not yet fit to the noise. So that's a kind of the property they have been using actually at the time. So therefore, what we were thinking at the time was that, okay, so now we have a deep image prior. So why not we just tackle the problem of denoising for this. So deep image prior was not really good for denoising. So it was okay, but it was not the best possible performance. So this was a joint work with the GIST from the Professor Jonghyun Choi. Well, so what we were doing actually is that, okay, we actually designed our loss using the so-called SURE, okay, the extended SURE that we just mentioned right now. And then instead of actually fitting to the input, now we are actually fitting to the some sort of like imaginary ground truth as far as we have Gaussian noisy image. Then in that case, what's happening here is that so the error will be backpropagated, but it will not fit to the noise, but it will be fit to the actually the estimated or approximated ground truth. So that's what we were hoping for. But of course, SURE or SURE has never been fitted to the, it never been actually used, for single image denoising so far. So we didn't really sure if it's working. But thanks to the regularization property for deep image prior, actually it was working quite well. And then of course we also had to design a couple of actually tricks to boost up the performance. So one is so-called the stochastic temporal ensembling, which means that, okay, so input, maybe instead of having just a random, we now have an input plus random. So actually that's not new. That has been out there for a while. But what we were doing at the time, what we were doing in this work is that just not just using one random and fix it, but we were actually changing this random noise over iterations. And this random even has a different noise level over iterations. So that's what we call the stochastic temporal ensembling. And then, this was actually working quite well to boost up the performance in denoising. So that's one thing. And the other thing is that because we were using SURE, we found that, they have some nice, zero crossing property around their convergence. So therefore, we were able to actually utilize that phenomenon to decide where to stop. So that's we call the zero crossing stopping criteria to determine when to stop so that the best possible performance can be out. So think in this way. So we don't know actually, when we have to stop because we don't have any ground truths, right? However, because of the SURE, we were able to actually estimate it using this criteria. So you can actually think in that way. So this is actually just a figure that we usually used to explain the deep image prior. So we can start from the T0 point, and then over iterations we can go to T1, T2, T3. So if we are using just a regular deep image prior, then eventually it should go to Y, which is the noisy image. However, if we are using deep image prior, the SURE, extended SURE, then now hopefully our algorithm will make will actually force to go to the instead of Y, but near X, not exactly X, of course, because SURE is also another approximation, right? Approximation for MSE. So therefore, it's not going to be X, but it will be pretty close to X. So that's what we were hoping for. So that's the difference between the deep image prior and our proposed method. So if you look at the result, then yeah, I mean, it's definitely a lot better than the BM3D, definitely a lot better than original deep image prior. And but compared with the self-to-self, we were not able to actually beat the self-to-self in terms of the PSNR. However, self-to-self is a lot slower than ours, very, very, very slow. I mean, but if you look at the different measure called the LPIPs, so LPIPs is the metric to actually measure the image quality. Then in that case, it's the lower the better. So we were able to actually get we were able to actually obtain the lowest possible result in terms of image quality. So if you look at all these patterns and the textures in the wood, and then you can see that those are recovered. It's not different. I mean, it is different from GAN-based work. I mean, SR GAN or different types of the GAN-based work. We don't know whether they are actually recovering the original texture, or they are just inputting the actual texture. But in here, we were not using any quality measure in our algorithm, but rather we were just using just principle-based MSE or approximation of the MSE. So therefore, this recovered patterns is a kind of the closer actually to the ground truth. Of course, it's not ground truth yet, but we are getting there. And if you actually, especially looking at this figure, so there's always a trade-off between. It's actually quite well known that usually there are trade-off between the PSNR and the LPIPs. So usually, if you want to achieve the higher PSNR, usually you have a worse LPIPs and vice versa. So therefore, S2S or the self-to-self actually show that trade-off. So it actually will getting better and better PSNR while it actually loses the performance in terms of the LPIPs. However, in our case, the star marking here, we were able to actually obtain quite nice PSNR, but extremely nice LPIPs number in this case. And you can actually see some good details recovered comparable to the ground truth in this case. It was also applicable to the Poisson noise, and then it was, it was for a quite simple example, but in terms of the Poisson, we were able to actually achieve the pretty nice PSNR result and LPIPs result too. So this work actually has been presented already at this year's ICCP this year. So by the way, the Poisson unbiased risk estimator or PURE has this following form in here. So we have a data availability term in here, and then we have a summation of the YIs, which corresponds to actually the noise, right? And then noise level estimation. And then we also have such a nice Monte Carlo divergence term in here. So we actually have the first order approximation term in terms of the divergence in here. And this work, of course, we were not the first to use this one, but we were using this one to for the different types of denoising, especially the CT denoising, and that was published in our Journal of Selected Topics in Signal Processing 2020. So if you're interested, you can actually see more formulation in there. So yeah, we've been talking about all these nice denoising works, unsupervised way, and then honestly, I must say that there has been so many works since then out there, noise to self, and all these other, great works came out, for the last couple of years, and I'm pretty sure that some works are quite outperforming our work, which is actually quite. It'd been great to see actually those works came out. But at the same time, that's not my goal. My goal is not really, achieving the best possible denoiser, but rather I want to use it actually to for the imaging systems, especially the medical imaging system eventually, right? So in that case, I believed in kind of the using a statistical model to deal with the noise and something like that. And then probably the next step that I wanted to actually see was that, okay, how can I actually incorporate these types of knowledge in the imaging system? And this is one example that, the usual camera uses the Bayer pattern, but, it's so therefore it's not really a perfectly spatially independent noise, but rather it's spatially correlated because of all the interpolation happening in the Bayer pattern. But you can actually unprocess it to make it to be independent again. So this is just one example, but it's possible always to deal with the original raw data. And I just want you to actually see if actually it's possible to apply those denoising in the imaging system. So one application that we found was the low-dose CT reconstruction that we published in our Journal of Select Topics Processing in 2020. One interesting part in here is the left side. So we have a projection mapping from the image to measurement. And then we have a filtered evaporation, which is the inverse mapping, right? From the measurement to the image. And these mappings are quite perfect as far as we have no noise. In other words, if we can remove noise, then we don't have to worry about the filter projection because it will just work quite well. At the same time, the filter projection usually, always have the ramp filter, which is a high pass filter. And that high pass filter can be, used as it is, as far as we can remove our noise, effectively. So therefore, our goal was to remove noise so that we can actually utilize the filter projection with the original ideal ramp filter in that case. So it was quite working well. This is really, small figure in here. But one thing I want to show you is that the first line, second line, third line is about different noise level. So the first line is actually really noisy. So I'm not sure actually you haven't seen this types of severe noise before. Usually you can see the middle or high noise, but even the high noise part, 10 to the power of 5 is not that high. Not that really a high radiation, but it still have some noise. Then PM3D works okay, and the deep image prior works okay, deep decoder works okay, but their denoising power is not really comparable to the ground truth. However, if you look at the rightmost side, that's a WMSC, which is the supervised case. And if you look at the supervised case, it's working quite well, right? And compared to them, we did this two different works, the W-SURE and the W-SURE fine-tuning are two different methods that we proposed. And then this is the case where we don't use any ground truth. Then in that case, our work was able to yield a quite good performance. I would say that there are still gaps between the supervised case and our case, but quite close compared to other competitors at the time. Moreover, if you look at this middle part carefully, then this red box, the top left corner, you can actually see some small bone structure, small bone fracture in here. You can actually see that in the original ground truth. You can see that actually in our proposed method, but it's a little bit blurred out actually in the supervised training. So this is actually another aspect that I want to emphasize. We may not be able to actually get the best possible PSNR or RMSE, but in terms of quality, it was okay, right? I say, without even ground truth. So that was the another part. So the last couple of minutes, last 5 minutes or so, I'll probably want to talk a little bit about the another case where we are facing the undersampled measurement. And then I'll wrap up this, talk. I'll wrap up this talk actually. So now this is a case where we have undersampled measurement. So we can just have this matrix A. And in this case, usually let's say that A follows the RIP condition. And I mean, X can be sparse, but in our case, it doesn't necessarily have to be. But let's say there's a sparse or something like that. Then in that case, the compressive image recovery problem will be the following: for given Y, can we actually obtain some X hat that is close to X? Then usual compressed sensing theory itself actually says that you can actually obtain the good, actually even exact solution for under certain condition by using this convex optimization with the L1 norm. So that was a kind of famous compressed sensing theory that was replaced now with the deep learning because of the computation time. Actually, the convex optimization usually is, takes us some time because of the iterative algorithm. So people have been working on this deep learning based computational imaging or AI based computational imaging by replacing it with the deep learning. And now the problem is, can we train this network? So now, as I said, this is kind of chicken egg problem. We have now A, which is the undersampled data, undersampled matrix. At the same time, we may even have a noise. So therefore, but let's say that even though we were able to solve this problem and then get the clean data, but it's not going to be ground truth anymore, but rather it's going to be an X hat, which is the suboptimal solution. So what we were trying to do was, okay, is there any better way to overcome this limitation or overcome this, dilemma? So we were interested in this special algorithm called the learned DAMP, learned denoising AMP, proposed by the Chris Metzler et al. In the NeurIPS 2017. And one interesting part about this algorithm is that they were using the unsages term, so that the intermediate result, which is the XT plus 8 Hermitian ZT, will be approximated as a ground truth plus Gaussian noise. So even though we don't know any noise, okay, we don't know any noise structure, just undersampled measurement. Let's say that even we don't have any noise, then this undersampled actually measurement itself will generate the Gaussian noise within this framework. So as we studied this algorithm, we realized that, yeah, maybe we can use this one with our SURE training. So that's what we tried. And of course, we were not the only one to try this idea. Actually, the Chris Metzler actually also tried this one, but our actually work was a little, has a better performance. So that, of course, at the same time, the Chris Metzler actually covers a wide range of unsupervised training. So that's kind of the difference. But what we were doing was that we actually, reduced the number of the, denoisers so that we can reduce the amount of, training time while having a similar performance. And then we train our denoiser with the MC SURE. And then we also change the noise level estimation equation so that we can have a more exact noise level. So in order to use SURE properly, actually, it is very important to accurately estimate the noise level. The previous work was actually fine for just applying denoisers, but it was not okay to train our SURE-based self-supervised training. So therefore, we actually had to change this. So the result was quite actually nice. For 25% sampling rate, we were able to achieve pretty good performance compared to the other computing method for Gaussian matrix. And this is a CDP, the coded diffraction matrix. The parametric property matrix for 15% sampling rate. This is MRI case. MRI case was we only were able to actually obtain the 40%, but it was okay. And this is actually another further works that I've been doing with the Roger Juris and the Yuna Yelda and others. We were actually also having an idea of the deep image prior, working with the generalized SURE for the blur in the immediate blurring and even super resolution. And we were able to actually get very nice convergence properties and very nice actually even the performance in terms of the image enhancement. And this work will be actually presented in the WebP 2022. So I'll actually I'm not going to go into too much detail about this, but rather please see this presentation in later, or check out our archive paper too. And this is actually another work I just submitted, which is the another case where, I've been talking about this, all the noise case. I've been talking about the undersampled data case or something like that. And this is a case where we are even correcting for scatter. And this is a case where we were using the physics models based on the short Monte Carlo simulation. So usually in order to do the scatter correction in spec, I mean, in many cases, we had to use the full Monte Carlo simulation, which takes us such a long time. What we were trying to do was trying to reduce the amount of the computation for Monte Carlo simulation, but compensate for it using the team learning. So therefore, this is a case where we have an Oracle, we have a full Monte Carlo scatter estimation, and this is the where we have a supervised scatter estimation. In order to do that, we still need a full Monte Carlo simulation actually to learn or to obtain the ground truth, right? The case that we did was that we were using this short MC scatter estimation, which takes actually 30 times faster than the original one. The overall actually 100 times faster. And then this one was enhanced using the team learning in a self-supervised way, so that we will obtain a very close result to the actually original full MC scatter estimation. So therefore, this is how the imaging physics can be utilized in terms of the team learning framework, so that self-supervision can be also done even for the scatter estimation case. So, I mean, my lab actually, has been working on these types of, model-based self-supervision. And then we are also interested in different types of works like video deblurring, pathology image, histology image analysis using team learning or even active learning. So we are trying to make a useful AI tools for different types of imaging and applications. So thank you for your attention. And if you have any other questions, feel free to ask me. Thank you.
Right. All right. Thanks so much, Prof. Seong Chun. I think that's really a wonderful talk. I mean, I learned a lot. A lot of denoising also is what I'm kind of focusing on. So really, that's a very fruitful discussion today. I think now we can move to the question and the Q&A session. So for those of you who have questions for Seong, please leave them in the Q&A, or you can just raise your hand. I mean, virtually raise your hand. I can unmute you and you can ask live if you want. And also, we will definitely welcome questions from our panel members. Who have a question, you can just go ahead and ask. Maybe I can start by just raising my questions, because I have a lot of questions. In fact, I realized that this kind of SURE thing is very powerful. I only came across that during my PhD, but I didn't kind of go into details. But I find that's really a good approximator for a lot of unsupervised learning and self-supervised learning scenarios. Mm-hmm. Maybe I can start by two questions. Maybe you covered that, but somehow I missed those details. I think this related to some of the two works you mentioned in early, I think the first half. First, I remember you introduced a variant version of SURE, where you kind of follow a similar setup than I think noise to noise, where it's not only you're not only have one noise, but you have two noisy measurement. Right. So I think you have a modified version of SURE that you have Y1 and Y2. Yeah, that part, and you prove that in fact the expectation becomes the same, or maybe okay. So one thing I'm not quite sure is yes, you're right. I mean, in principle, if you have Y1 and Y2, and then you prove that, say, if Y1 equal to Y2, those two becomes identical. But what is actually because you also show that empirically, using that variant version of SURE kind of improve the denoising result comparing to just using one, right? Then what is actually the contribution or what actually make this denoising result better? I mean, by just replacing the conventional SURE with the variant version. I mean, I see some theoretical results showing the equivalent, but what is actually making that better? So maybe I missed that part in your presentation. Yes.
Yeah, that's actually a very good question. So the question that we had at the time was that, so let's say that we have an imperfect ground truth, and then let's say that we want to train the the denoiser, then we always had to add a noise because the input requires high noise. Then what we were actually wondering was that, okay, so we have this such a nice, imperfect ground truth is definitely better than noisy image, and we just curious about why we cannot use this, right? So therefore, that's a kind of the starting point. And then one thing that we found was that, okay, this data fidelity term is quite important. So in the past, when you have a just SURE, then this Y1 here will be just same as just Y2. Then in that case, this data fidelity term, will be, noisier, I say. So therefore, in order, by using them, this is just a still approximation. So therefore, by using Y1, hopefully will give us the better, estimator. In here, better means, lower, I say, the variation. So therefore, I think it was working better than the original SURE. So in terms of the mean value, they should be the same. But in terms of the variance of the estimator, they should be different. We didn't really prove it at the time, but I cannot really prove it yet. But I think that's a kind of the hunch that I'm having.
I see. No, I get it. Right. So yeah, I think that you're right. I think it comes from there. Like you have two noisy measurements. Hopefully that can reduce the variance. Then probably that becomes a better approximator. Then yeah, okay, that makes sense. Mm-hmm. Okay. Actually, my second question is about, I think, the work after this one. Like you combine the DIP, deep image denoiser, deep image prior, with SURE. You kind of replace their loss function where they directly do an MSE between the output and the noisy image, but you replace that with SURE. Okay. Also, maybe I missed that part because my understanding is that SURE only, all of the proof only works for Gaussian noise, right? But I remember DIP, they demonstrate a lot of inverse power, like impending or other than Gaussian noise. Right. Does this kind of thing works for others as well, or only works for Gaussian denoising?
So that's a very good question. So SURE for now. So the thing is, like, we need a really accurate noise level estimation. So therefore, it has been shown will work well with the synthetic Gaussian noise. But we actually have never been tried the real noise, real Gaussian noise yet. So, for example, in camera imaging, usually it requires you to, estimate the noise statistics for Poisson plus Gaussian, but we didn't really find a way to accurately estimate the noise level yet in order to train or in order to utilize the SURE, properly working. So that's a kind of the actually limitation that we have for now. But however, for Poisson, it was working quite well. It actually has been applied to the synthetic CT, but now actually we are working on applying it to the posterior emission tomography. So in that case, it's working for the real data right now. So in some part, it's working with the real data, some part is not. So in this particular paper, we were all doing synthetic noise. So the argument was that deep image prior was working very well, but it was not really performing well only for the denoising. So that's what we want to actually resolve. And the problem, in that sense, so that this is kind of the focus of this paper.
I see. Yeah, that makes sense. Yeah, because I thought like this can magically extend it to like penny, all of other things. Yeah, I couldn't figure out the reason why the theory can extend it, but I think that makes sense. At least for denoising, I think that's definitely a better choice than just do MSC. Yeah. Okay, great. Thanks so much for the clarification. Okay, now I think I don't know if any other question. Oh, Dennis. Yeah, go ahead, Dennis.
Okay, thank you. Thank you. So this is a very nice talk, by the way.
Thank you.
I appreciate it very well. So I have just one quick question, which is more or less similar to the one asked by behind. So because in all your model, you are assuming an additive noise. Okay, sometimes it was Gaussian noise, and sometimes it's and in the result, you show some result with Poisson noise. So I'm wondering if you use some kind of transformation between Poisson and Gaussian or not. So can you elaborate a little bit about that?
So your question is, how can we extend it to the Poisson?
Yeah, because you show some result with Poisson noise. So I'm wondering how you perform this. Did you use some transformation from Poisson to Gaussian or not?
So we actually specifically use a different, so SURE is usually for, it's only for the Gaussian, but there has been actually a lot of different extension work in the statistics. And also actually one of my collaborator, Yunina Elder. So what happened there is that there is a form of the SURE for the Poisson noise, so we call this pure, And then there is also a form for the Poisson plus Gaussian too. And there is also work for the Riccian, and actually the generalized SURE is for the exponential family. So it has been actually a lot of different models, but we just didn't find, I mean, we are still working on going towards like, covering the more noise models. So pure, I mean, my answer for that is basically we are using different form of SURE for the Poisson.
Okay, nice. Thanks.
I see. Yeah, I mean, I didn't know that there are many variant versions of SURE, but
oh yeah, there are a lot more.
SURE.
Right, Riccian and to all these different works. I mean, so there are a lot of actually works, and then yeah, so hopefully we can actually reduce the gap between the real noise in the even camera imaging and the synthetic data. But for now, we've been successful for only for the Poisson part for the real data set yet.
Okay.
Yeah, but I think that's a really direction to explore, right? So I think most people working on the network architecture, but the loss function you can also play with all of these approximations and quality assessment. Sure, that's a good angle. Okay. Yeah, I don't know. Any other question from our panel member? Like
there's a chatting board. Can this method be adaptable to non-noise like disturbances in ground truth? My answer is that as far as they are close to Gaussian, maybe yes, but it may not be actually working for the non-Gaussian part for now. So in that case, hopefully we can extend different models, and then based on models we can actually adapt to the different disturbances actually. But the non-noise like disturbances, I'm not sure about that actually. So I don't think it's gonna work that well. Yeah, so that's my answer. And then
there are two more from the Q&A.
Right. So one is the noise-to-noise work, how the Y2 images were generated. So Y2 can be generated in many different ways. So one way is Y1 plus noise will be Y2. So that's one way. The Y2 also can be generated, for example, let's say that you have a noise-to-noise setting, then in that case, you have two independent noise realizations, and then average of them will be Y1. And then just choose one of them will be Y2. So those are the scenarios that we actually explored in our 2019 Mirrors paper. So in real experiments, such as the problem of motion artifact in MRI. So yeah, if you have a motion artifact, then the problem will be, we are assuming that we have no motion actually between two realizations. So therefore, noise, that's actually weakness of the noise-to-noise in my mind, because you had to anyway acquire the two independent noise realizations. So in that case, it requires more time to acquire. So therefore, it will be a prone to noise artifact. So therefore, it's kind of the a little bit of the weakness of the noise-to-noise. But in the case of the SURE, we just need the one realization, so we don't have to worry about it. So yeah, but of course, worry. I mean, a little bit worry, of course, but yes, relatively. So that's a kind of the question. And then another question is, I think, two questions. Applying medical images using an accurate noise level will be important. Is there a good way to estimate? Yeah, so that's a very good question. So noise estimation is still the part that I'm working on right now. So I don't have a good answer for now for that. I mean, so some part, yes, I have the answer, but in general, not easy. But only for Poisson noise, we don't need to estimate noise. I mean, the image itself will be actually the noise itself, right? So the Poisson noise usually have a variance of the the variance of the mean, right? The mean of the Poisson will be the same as the variance of the Poisson. So, from that equation, actually, we don't need any noise estimation. That's how I think Pure was working actually okay with the real data. So that's my answer. And then what if we use the inaccurate noise levels? Usually it's not working that well. So as far as we understand, noise level should be actually very accurate. But if it's not, then it has some different behaviors for different networks. So we are still exploring that part. So I don't have that good answer for them now.
Yeah, I think there are another entire community working on noise estimation or noise level estimation. But yeah, so perhaps you can check out the relevant literatures. I know a few, but I think nowadays people will have deep learning to estimate as well. I mean, there was some conventional method.
That's right.
Yeah.
That's right. Yeah. So we are still working on that too, right? Yeah. I noticed that.
Yeah. All right. I think we got all of the questions. Unless any of you have any follow up, yeah, you can always maybe email Prof. Sion for more clarification.
Oh yeah, of course. Yeah, I have an email address here.
Yeah, and also you can read the papers. I think Prof. Sion give all of the references there. You can check out more details on the papers in the list. Okay, so then if no more question, we would like to really thank Prof. Sion for giving us the really nice talk, and I think most of us find it very interesting, and we're very excited to see all of these results. So I mean, again, thank you so much, Prof. Sion, to come to our space webinar. I think this is probably the last one this year since it's December. Yeah, we definitely wish to see you in our future events, and thanks so much for the great contribution. Thank you.
Oh, thank you for having me. Thank you very much.
Great, thank you.
Thank you.
Thanks so much. Thanks.
Thank you.
All right.
Great
Thank you,
Bye-bye.
everyone. So
Great to meet you all.
Bye-bye.
okay, so that'll be end of this seminar. So thank you so much, and yeah, hope to stay tuned for other events from our CI